and would like to introduce Professor Clara Saraceno from, like I mentioned, Bochum University in Germany. She is a leading expert in high-power, ultra-fast lasers and their application in terahertz science and technology. She also has won and received multiple awards, even including last year's RC Grand. So with huge applause, please welcome.
All right. Can you hear me? I did turn it on though. Do you hear me? No. Ah, yeah, there. Perfect. All right. Thank you very much for the introduction. So yeah, today I'll talk a little bit about our work on high-power ultrafast lasers and how we're trying to use them to generate terahertz light. And I'm from the University of Bochum. And in fact, I mean, there was a nice introduction before talking a little about career. And I always like when it's a student audience to reflect a little bit on how I ended up doing what I'm doing. So I put an arrow of experiences that I had when how my career evolved. So I actually moved a lot. I'm originally from Argentina. I studied in France. I worked in a company in the US, you know, Coherent, probably, that now basically all their lasers are being replaced by light conversion lasers. So anyway, so no. Then I moved to Switzerland for my PhD, then stayed a little longer and moved as a professor to Germany, where I'm working now on these high-power terahertz sources. In fact, it was not really a straight line. Well, I guess what I wanted to point out is, well, this is my scientific career, but most importantly, I'm also the mom of 3 wonderful children. So I'm always happy if like young people come and ask me, because I have quite some experience of juggling work-life balance. And so I'm happy to talk about it as well. So because the University of Bochum is not very well known for optics and photonics, I thought I should introduce where we are. So we are here actually very close to the Netherlands, right in the middle of Germany. The Ruhr area is quite particular in Germany. It's actually the most populated area in Germany, with about 5 million inhabitants within like 3 or 4 cities and one huge megalopolis. We have many universities there, and the University of Bochum is the largest one. And it's interesting because it's the first post-war university there. So it has a lot, also since it's a working class environment, lots of first-generation academics. So it makes the population really interesting to work with. And it has very strong areas of research, which my group is part of. Especially the chemical sciences is very strong, because there's a very strong history of chemical industry. So, and one important thing also, since we have the proximity with all these cities and with all these universities, we have the University Alliance, which is an alliance of universities that's pretty much within 20 minutes one from the other. So that makes it very nice for making education programs, etc. So, and in this context, then I fit well into the chemical sciences, because we develop sources, and those sources are important for spectroscopy, exactly for these areas. So this is my research group. We are actually in the Faculty of Electrical Engineering, and my group is kind of divided in 2. There's a subgroup that really works on terahertz technology, and now more and more as we develop the sources in terahertz applications. We have a part really building lasers, and we have now a spin-off team that's trying to commercialize part of the lasers we develop. And my husband actually specializes on numerical simulations in ultra-fast science. So this is what my team looks like. And I divided my talk like this. So this is kind of an arbitrary division. In principle, I had put actually no division initially, and then I thought, okay, it's too long to make it without divisions. But you'll see how it all merges together as I speak. So first of all, very briefly, because I think in this crowd, it's an incredible honor to talk to people who already understand what an ultra-fast laser is. But I thought it's still important to highlight how important and relevant these high-power lasers are, and in general, lasers and ultra-fast lasers. Then I'll talk a little about the high average power laser technology we work with, and then their application for terahertz light, and then I'll give a little bit of an outlook of how we're moving forward to make more progress. So I always put this nice slide. It's a little outdated, actually, but I find it extremely humbling to think that I work with lasers and that I'm working like at the cutting edge of laser technology, because lasers is something that allows you to go into wherever you like. I feel like I've always been kind of at the top of the pyramid. So many people need lasers and advanced lasers, and it's such a luxury to understand how they work and to be able to tailor them for the application that you need. So in fact, many people in other fields maybe don't realize how incredibly important and how like lasers affect so many aspects of our daily life that we might not think about all the time. And so the type of lasers that we work on are these ultra-fast lasers that generate these very, very short pulses. So we're talking now about electric field kind of bursts around picofemtoseconds and peak powers around mega to gigawatts. And at this point, I'd like to tell you an anecdote. It's funny. My father is a theoretical physicist, right? So when I wrote my thesis, I was working on these kind of very high average power ultra-fast lasers. And I told him like, hey, would you read my thesis and tell me if you understand anything at all? He said like, well, wow. What really impressed him is megawatt peak power, right? He is a person who never thought that that was possible on the tabletop, right? And in fact, when you think about what this means, it's actually quite impressive. So when you have a gigawatt laser or a megawatt laser, this is the type of peak powers that you generate from a nuclear power plant. Of course, you generate these continuously, right? So we do this only for a short amount of time, but still, so for him, this number, megawatt, gigawatt, was something that was impossible to think about from a tabletop source. So if you think about the things you can do with that, that's actually already impressive on its own, and it explains all the different applications that you can do. Of course, then the very short time scales allow you to then also understand and explore these very fast dynamics. In fact, many people use these ultra-fast lasers to do ultra-fast spectroscopy in a similar way to flash photography, right? So we always think about this, well, we are limited by the flash duration at some point, and we want to look at things that move fast. So if we have shorter flashes, we can look at faster processes. In fact, the idea of doing this flash photography is really old, and the question is a little bit like, okay, flash photography, it's not really true, because there you're limited by the flash duration, but we are looking at femtosecond phenomena with femtosecond lasers, and this can easily be done using pump probe setups. And in fact, I would say probably most of the ultra-fast lasers out there are deployed to explore even femtosecond or sub-femtosecond speed phenomena, even if your pulses are femtoseconds, because there you're actually mapping your time into a spatial delay that can be even shorter than your pulse duration. Okay, so this allows you to study very fast dynamics. This is the temporal aspect of ultra-fast lasers, and this allows you to study a lot of interesting things. We all know also these temporal, very short pulses, if you look at them in the spectral domain, they correspond to a superposition of many, many modes. And these modes basically are millions of frequencies that come together in phase at one point in time and build up coherently to make these very short pulses. So that means also with this, you can see the ultra-fast lasers as a superpositions of millions of frequencies for which you can do broadband spectroscopy, right? And this was the field of frequency combs. This is like a ruler basically in the terahertz. Okay, so now I guess I'm not teaching you much so far. I just basically want to communicate my excitement to you of all the possibilities you can do with such lasers. But most importantly, and I think this is something where you'll see in the rest of the talk, it's the aspect we use mostly in my lab, is with these femtosecond lasers, we can achieve extremely high intensities, both because you can focus the beam temporally and spatially. So this allows you to excite, modify all sorts of nonlinearities up to the point where you can actually modify the materials or drive nonlinearities, generate new colors, etc. So it opens up not only the field of material processing, which we know quite well, but also opens up possibilities, huge possibilities in nonlinear optics to access spectral regions that are normally not accessible directly. So this is what I'm going to be talking about today. So the trend now is we have a lot of lasers, ultra-fast lasers, that are, say, in the near infrared and are starting to approach neighboring regions. But we want to go to regions far away in the spectrum where we don't have lasers that emit directly. So this can be done, for example, for XUV radiation via high harmonic generation to go into the high photon energies, or you can be interested in applications where you go to lower photon energies like I do in the terahertz. So, and the trend is quite clear. We have higher average driving power. We want higher power than in these spectral regions. It's as simple as that. So this is a lot of what my group does, is trying to understand which are the best laser technologies to do this, and how do we translate that power we have now in the near infrared into these exotic, faraway spectral regions. Okay, and I mean, in case I was not convincing enough yet, I think it's worth reflecting why these technologies are important. I mean, it's clear that there are several Nobel Prizes recently that were given to really technical advances around ultrafast lasers, right? And I mean, actually, I put this picture here because this is cute. It's a vacuum chamber that is in my lab now, where we have 2 signatures of 2 Nobel Prizes in one of the vacuum chambers of the lasers that we have in the lab. So that's actually quite nice. In fact, it turns out it's 2 women Nobel Prizes, the very rare women Nobel Prizes in physics. Okay, so now enough with the general introduction. So I want to talk about the high power laser technology, how we got there to where we are with these very high average power driving ultra fast lasers. Why are people excited about high average power? It's very simple, especially in fields where you need a certain minimum amount of pulse energy or peak power per pulse. And in the end, you are measuring perhaps averaging over many pulses or measuring many, many weak signals. You need a higher repetition rate in order to even maybe make your measurements possible. So this is what high average power brings you. So if you need a certain amount of pulse energy or peak power in one single pulse, and you increase your average power, then you simply have more pulses per second. You can do better statistics, and you can get higher signal to noise ratio. So, and this applies kind of universally to most, at least in nonlinear optics, most generation methods and most experiments that you might do with your light afterwards. So of course, then if you can measure faster, you can measure more complex samples, you can measure more samples, and you can consider doing experiments that maybe before you were not trying to do or you could not do at all. So this is why people are trying to move more and more into high average power lasers. Now, the good thing is throughout the maybe last 20, 30 years, there's been huge development in this area. And now I would say we have actually lasers that even are so powerful that we almost find it hard to use them, right? So this is the realization is I would say the field of high power ultrafast lasers has moved faster than the applications can catch up. So this is the situation we are now, where we are trying to see how can we use these lasers. So the key is, in principle, if you forget about the ultrafast, you want to first have enough continuous wave power from your laser, and this you can achieve by having good surface to volume ratio in your gain medium, and additionally having gain materials that have on it their own good thermal properties, like for example here ytterbium YAG, you see you pump and you lase pretty much at the same wavelength or very, very close by. So intrinsically the heat that's generated is low, and plus it has other advantages for making geometry suitable for power scaling. So, and these have been exploited a lot, and so I'll not go each one into detail. I actually want to talk about one specific one, which is the thin disk laser technology. If you take a look here, I plotted in these ytterbium high power ultrafast lasers here pulse energy and repetition rate. You see what has happened in the last decades is all the old lasers that used to be at around a watt are now moving to 10, 100 in a kilowatt. In fact, light conversion and Lithuania in general has played a super important role in this, because now we have at 100-watt level lasers that are extremely stable and industrially mature, right? So this has completely changed the picture of what people can do in the lab. And this is really very, very valuable, I would say, because people are used to ultra-fast lasers in many communities are scientific lasers. Now all of a sudden we have all these wonderful industrial lasers that work really well, right? All these PhD students can now save so much time because they actually have good lasers in their labs, right? So they can finally focus on the problem at hand with their lasers. Okay, and what this has done is basically across the repetition rates from not so high to very high, we now have either very, very high energy levels or many, many more pulses per second with significant pulse strength. So, and what we explore is what opportunities does this open for terahertz science? And I mean, in fact, one of the big bottlenecks, the reason why these technologies took very long to be adopted is because, well, you saw it in the graph before, ytterbium YAG is wonderful, for example, but it has a relatively narrow emission bandwidth. So the pulses you get out are typically some hundreds of femtoseconds. They're not very short. Okay, so in fact, I think one of the big things that changed in the last few years and why now it's easier, at least in the scientific community, to make use of these ytterbium lasers is that someone had the wonderful idea that you could do at hundreds of watts of average power, a nice scheme to do free space pulse compression. So I used to work like maybe 15 years ago on trying to compress lasers with ultra short pulses and hundreds of watts of average power down to sub 100 femtoseconds of 50 femtoseconds at hundreds of watts by coupling them into hollow core fibers. And this was probably the worst time of my life because all the fibers would burn all the time. It was ultra sensitive to coupling, ultra sensitive to the quality of the beam of the laser, and it was an absolute nightmare. So someone came up with this idea, well, in principle, you can kind of emulate what's happening in a fiber by making what they call a quasi-waveguide. So if you use, for example, a Harriot cell type arrangement, and you have spectral broadening introduced in the way of a plate or in the way of air inside the medium if you have enough pulse energy. In fact, by multiplying the number of passes, you're doing the equivalent of a waveguide, but you're leaving enough time for the pulse to propagate in air such that the beam doesn't collapse and ruin, either damage or ruin its own spatial mode. So this was really, really successful. And in fact, it's very, very versatile in the kind of things you can do. You have a lot of degrees of freedom. You can change the nonlinearity, you can change the nonlinear medium. You have a lot of design freedom to do very good pulse compressors now with these ytterbium lasers. So this has really opened a lot of possibilities also for us in the terahertz field. And you'll see later when I get to the results from my group that often we have a little compressor after the laser because we, of course, want to get bandwidth there, and that helps. So the key of why this works is actually pretty simple. So you want to avoid self-focusing, right? So the key is what you want to try to do is you end your nonlinear medium before the self-focus happens, right? Instead of having the beam collapse too early inside your medium, because this is a kind of self-catastrophic effect, right? So you have a higher intensity and then the beam gets smaller and then the beam gets even smaller, the intensity gets higher, etc. You cut the nonlinear medium early enough and you let it propagate a little bit. And this really avoids this kind of collapsing effect and the beam degradations associated. So you can divide this to make multiple passes, and this heals the beam automatically. So that's the key thing. And in fact, if you use, for example, this in combination with thin disk lasers, now you can reach really, really high pulse energy short pulse amplifiers, or you can do, for example, directly mode lock lasers with high power, which is what I want to talk to you a little bit more about. So now, maybe you are familiar already with the thin disk laser and what the concept of a thin disk laser is. So the idea here is how to reach very high power levels. We have a gain medium now that is very, very thin. And thin means thin compared to the beam size, right? So we have more or less a factor of 10 between the pumping beam and the thickness. So that means that if you cool from the back, if you have a good heat sink, you can basically have a one-dimensional heat flow through the back and pretty much have zero thermal aberrations. So you can, in principle, scale your power out by scaling your pump spot and your cooling area correspondingly. So that, of course, on paper works great. There's some technical limitations of that. But to achieve actually efficient pumping of such a geometry, of course, since the medium is very thin, you don't absorb much in one pass. So then you need to go many, many times over the disk. And this is typically what you do with a kind of parabolic mirror arrangement. Okay, so this is what we're going to be looking at. And I wanted to point out here, you have this good pump absorption because of this multi-passes. You have a very thin gain medium. So what it means is you have pretty much zero nonlinearities if you build a laser with this. So the only thing that's bothering you here, you have a very thin, very large mode area, and you have air. So maybe you add a plate for conserving the polarization, etc., but pretty much your nonlinearity is zero. So that's why you can scale up the energy massively in this geometry compared to, for example, using fibers or using other type of laser geometries. So this is really, really, I would say, ideal. And I have a video, it's just cool to watch, so I have to show it. So you can once understand how the thin disk laser geometry actually works. So you actually see here, you have actually your disk is sitting there at the focus of a parabolic mirror. Your pump is typically a very low brightness diode pump. And at every pass, the disk will absorb maybe, I don't know, 10% of the pump radiation. And in order to pump it efficiently, then you just need to go many times through the disk medium again. You come at an angle so that you can actually build a resonator then through this hole in principle. And of course, now these kind of laser module heads for pumping are commercially available. We don't build them in the lab ourselves. You can buy them. This is the example of 24 passes, but you can make them up to 72 passes or even more now. So you can make the discs thinner and thinner and make more and more passes. Now, at the last pass, you can, for example, add their retroreflector and then pass all the number of passes again to absorb even more. And so then we build the laser around this geometry. So the most common use of these lasers is actually to use them to build chirp pulse amplification setups. So if you have this very high average power, you can, in principle, then use the CPA geometry and then just scale the energy pretty much massively as much as your average power allows you. So this is what people have been doing. This is not the research that I'm doing, but most cases what people do in this case, just to give you an idea of what the state of the art is since we have this low gain per pass, then for your amplifier, you need to have some kind of multi-pass geometry. So either they build geometrical multi-pass geometries or they build regen amplifiers. And in fact, so one of the things that now has become commercially available, there's these scientific systems now that are available with this type of systems that are reaching up to 200 millijoules of pulse energy. So this is actually pretty crazy. These systems are now pretty much only scientific from what I understand, but still they enable a lot of things in the lab. So for example, applications like electron acceleration, et cetera, because of the really massive amount of energies, right? So this is, I think, pretty exciting. Okay, so but what we are doing in my lab is we are actually working with this technology to build oscillators. So not so much super high energy CPA, et cetera, but rather say, okay, well, we have a technology with which we can get high average power. So in principle, nobody prevents me from taking that laser and mode locking it and getting directly ultra short pulses without needing any amplifiers. So of course, this is a different operation range. So here we're talking about repetition rates in the kind of megahertz with very high, let's say a high energy for megahertz repetition rate. Okay, and so I think this is kind of maybe the future. These systems are not commercially available, but they can generate from a single system like hundreds of watts. And I'll show you a little bit what one can do. So how does this actually work? It's quite simple. It's really like and I'm probably sure that everybody here studied lasers and mode locking at some point during their bachelor's or whatever. So it's really like a standard solid state laser mode locked. Nothing is different. Only the gain medium is now a disk. And you can add some kind of saturable absorber to make this pulsed, right? Now, what is maybe a little bit special is now we have output powers of 100 watts or hundreds of watts, and now we have intracavity powers of hundreds of kilowatts. So this comes with some fun challenges, right? So here in the example of KLM, this is the typical solid state laser mode locking picture. The gain doesn't saturate pulse to pulse. Your loss follows pretty much exactly your laser pulse. And so in the end, what happens is the gain net window that forms is as short as your pulse. So specific to the thin disk geometry, as I mentioned, we have low gain per round trip, and we have long and sensitive resonators with large mode areas, which has really special challenges in how we design these lasers. And just for fun, this is 2025. This type of laser, the first time it was demonstrated was in the year 2000. So this is kind of the 25 years that this technology has been going on. And the progress that's been made is really huge, especially given that this has been pretty much only done in academic circles. There was not so much interest from industry yet to put their hands into building a 500 watt mode locked laser because the rep rate is very, very high, right? So it's probably still something that will be adopted in future when we start needing really multi-kilowatt amplifiers, maybe as seed lasers or something like that. So in this nice laser, actually, turns out that right now, the situation where we are is we have average powers up to 550 watts. So the growth in average power has gone up by a factor of 35. the pulse energy has gone up by a factor of pretty much like 200 since this first demonstration. So, and we have pulse durations now. We've made a lot of progress, and even with the terbium YAG, we can now get pulse durations as sub 50 femtoseconds quite easily because we've really understood how these lasers work. And this is actually really, really a nice platform for doing nonlinear optics. Because at this point, I want to insist, like, we care about this for then generating terahertz light. This is really from a single box, you get these perfectly beautiful second hyperbolic squared pulses, right? Phase is absolutely perfect. It's like a textbook soliton, right? So that for doing nonlinear optics and then for further expanding the beam or for further expanding into other spectral regions, etc., this is really, really helps to have a good seed, right? I think everybody that builds lasers know it all starts with the seed. If your seed is crappy, your laser will have trouble in the end. So a good seed is really critical to get all these systems, even if you're going to use this just as a seed for a higher power amplifier. Okay, so the challenges that we face in this technology is, I said it before, we have these resonator designs with very large modes. So what happens there is the stability zones in the laser then shrink. So that means if you're targeting a certain spot size to have a good overlap on your disk, the more thermal effects you have, the more you will be off very quickly and your laser will get multimode. So this is a big problem. So you have high sensitivity on thermal effects, etc. And we have huge requirements on the quality of the optics and all the thermal effects on all the mirrors in the cavities. And thermal effects also and damage are a big problem as well, right? So as we have these really high peak powers and high average powers intracavity. So for example, I plotted here, this is a typical resonator in this geometry. And you see here, if I heat up one of the end mirrors, what happens with the cavity? So you see very quickly that, for example, if my disk is here and I need to have a certain spot size, right away when my optic here is heating up, then that results in a complete change of mode, which means my resonator will become completely multimode and will freak out and not work anymore. So this is the kind of challenges we do. And we've worked a lot over the years to improve the situation. And we have, in fact, now really, really good ytterbium disks for this type of lasers, which has helped us to really move forward, right? Because this is one of the main challenges. If the disk deforms while you're pumping it, then you can forget about doing stable mode locking. And we have also worked on making better CSEMs, better absorbers, et cetera, that have higher tolerance to average power and to peak power as well. Okay, so we moved along, and then the other problem that we really face with this, as I've mentioned before, we have these lasers, huge intracavity power, huge intracavity peak power. The nonlinearity gets so high that the air starts to limit you. So you cannot get higher power levels because your air becomes nonlinear at some point. And then you have too much self-phase modulation, your mode locking breaks down. So how did we do then? We moved from flooding the cavity with helium, which helps because the nonlinear refractive index is lower, to trying to reduce the intracavity power in the oscillator by multiplying the gain, to then simply just saying, forget about the air, we build the laser in vacuum. That's a luxury that in a fiber you don't have, but it is still a bit of a luxury. I think there's still some work to do on trying to come up with clever ways of avoiding the nonlinearities in these lasers. But so we move then from these 10 microjoules to these 80 microjoules. And now, where are we standing? So this is the latest result. It was done in the labs of, where the previous labs where I was working, using pretty much the same technology we were using around 10 years ago. So it's still an ytterbium YAG thin disk laser. It has multiple passes on the disk to minimize a little bit the thermal effects intracavity. It has a heat-sinked, very carefully designed, high damage threshold semiconductor saturable absorber mirror. And the record now is this 550 watts and 5.5 megahertz, 100 microjoules. And this is all from a single oscillator, right? So this is quite a nice platform for doing now nonlinear optics with this laser. I think this is the takeaway from this laser part. And this is the laser, by the way, that has the nice signatures. It's nice. So, in fact, that laser was built at ETH, and now it's sitting in my lab because my previous supervisor, Ursula Keller, if you saw her ever, I think she gave a talk here a couple of years ago. She actually continued that development. Now I think she retired. And so she gave me that laser to continue doing experiments. So I'm very happy about that. So, okay, so now we have this fabulous technology. Now let's use it for generating terahertz. So in fact, our motivation is the following. When you have these ultra short pulse lasers and you say, generate using, it can be any, for now, generic nonlinear method, these very short terahertz pulses. Why are we interested in this spectral region? Well, terahertz frequencies correspond, in case you have not thought about this, 1 terahertz is 300 micrometers. Okay, why is high power important? You see it already there. So we convert light from 1 micron to around 300 micrometers. So we go really, really far away in the spectrum. So that means the conversion efficiency is garbage. No matter what you do, even if you convert 1 photon to 1 photon and use cascading to generate more than 1 photon with 1 photon or whatever, if you have 1% conversion efficiency, you're in the winning leagues. So this is really a case where if you need high average power at the output, you really need high average power at the input. Right? So this is what motivated us to start looking at this. And these terahertz frequencies are actually very interesting now for various reasons. So one of them is, if you know a little bit about electrical engineering, you know that people use radar to do inspection and non-destructive testing, things like that. Terahertz frequencies are higher frequencies. In principle, they give you much higher resolution, but they still see through most objects that are opaque optically. So you can do lots of really nice inspection scenario. The very short pulses on top of that have a very broad bandwidth, like you see here. And so you can, on top of that, get signatures of the materials that you're looking at, right? So you can, in principle, do multispectral resolved images if you could acquire the pulses fast enough. There's another community of people that are looking at these pulses to do spectroscopy, and this is what we are mostly interested in, just simply because we have the community there in Bochum. These very tiny photon energies are actually really, really good to do condensed matter spectroscopy because they hit, for example, phonon modes, they hit in certain larger molecules rotational vibrational modes, etc. And so there's a lot of interesting physics to be done there in condensed matter. So now, okay, we generate these very short pulses. I'll explain how we generate them in a few slides. If we manage to generate them with enough field, then we basically have a very short, ultra-fast modulation of whatever material properties that you're exciting. That's what people are really excited for with these terahertz pulses. They are like an ultra-fast switch. And you can do, of course, time-resolved studies if you do, for example, pump-probe experiments or multidimensional spectroscopies, etc. Now, the problem is commonly accepted from this community is like people are so encrusted that this you can only do if you reduce the rep rate. Because you need a strong field driving pulse to generate your nonlinearity, to then generate your terahertz, you can only do this at a kilohertz. So this has been in people's minds for very, very long. And this is where we thought we should change the situation. And just to give a little bit more insight of why it's so important to have high average power for this specific field, rather than saying, oh, well, yeah, we need for signal to noise ratio like I did before, I want to give you more clearly how the detection of these pulses works, which then explains you why we really care about increasing the number of pulses per second. So the way we do this is typically we have, this is our near infrared pulse. I had to do it green because, well, terahertz is even more red than near infrared, so I had to do some color that looked like a higher frequency. So most of the setup looks something like this. So most of the light we use to generate our terahertz pulse, and a fraction of it, we use it in a sort of pump probe setup to actually detect the field coherently. Okay, so this is the case of what we call electro-optic sampling. And in this scenario, what happens is, well, this is typically has an electro-optic crystal. And so what happens is the terahertz field changes the polarization of the probe proportionally to the driving electric field. So as your terahertz field changes, then the polarization changes simultaneously, and you can measure that directly in the near infrared. And that is really beautiful because, well, we have really terrible detectors in the terahertz. And here you are measuring directly in the near infrared. Right? So you circumvent the problem of dynamic range, et cetera, of measuring with terrible incoherent power meters in that spectral region. Okay, but so of course the drawback, this is beautiful, right? You measure directly the electric field, right? You all know about ultrafast, it's like normally you don't measure the electric field directly, right? In this case, we can really see the electric field in phase and in amplitude, so of course then we have a really powerful tool. So now, of course, the problem comes how we reconstruct the pulses, right? So we need multiple time-delayed probe pulses. That means the refresh rate of our terahertz is really slow. right? So normally if you use a mechanical delay, we're going to be acquiring at, I don't know, 10 hertz, if we're lucky. So if we want to improve that and use methods that are fast, we need more pulses per second. If not, then we integrate for really long times, and that takes you all your time. And if you want to then increase the number of dimensions and increase the number of samples, then you're in trouble. Okay, so in my lab, we are doing that then. So in a nutshell, we develop these mode-locked in disk oscillators. For example, we have other high average power lasers as well. We do high average power terahertz generation, and then we apply them in some average power hungry applications that we have around in our environment in Bochum. One of this is solvation science, and this other one is in imaging. We have another consortium of people working more with electronic sources that are interested in seeing what the limits are if you go to very high powers. So I'll show you two examples then now of why. And so in principle, so this is how I started into this field. It was just really someone came to me and said, hey, we have this problem. You do high power lasers. Can you work on this? Is there a way out, right? So in Bochum, we have this cluster of excellence called Resolve. These are a lot of scientists that are working to understand the role of solvents in chemical reactions. So it turns out that for many decades, people thought of the solvent in a chemical reaction as being kind of a passive actor. And in the last few decades, it's more and more recognized that it's not a passive actor. It actually influences a lot of things. And water is, of course, we all kind of know it, the most important solvent that we need to understand because it kind of affects how our body functions. But water is horrendously complicated to understand. It has all these really, really complicated coupled motions due to this hydrogen bond network. And you see that this hydrogen bond network happens in the picosecond timescales. Picosecond timescale is 1 terahertz. So it turns out to be that in order to really understand this problem, what you need is good terahertz sources. And in fact, of course, it's great, but it absorbs a lot also in the terahertz. So you not only need good sources, you need also high power sources in order to be able to do advanced spectroscopy, like multidimensional spectroscopy, et cetera. So we ended up getting into this area, interested by this kind of curious problem where people were lacking the right high power technology. We came from a laser background, so it was a good fit, let's say, for our research. And just so to give you an example, this is the type of experiments where we think the sources we're building now can really make a difference. So I don't like to leave things like, oh yeah, solvation science and its high power is great. So I want to give you one very specific example of where the high average power can make a difference. So this experiment is called kinetic terahertz absorption spectroscopy, KITA in short. The idea here is the following. You have basically a protein surrounded by water at room temperature. You put it in a cell and you put a temperature jump to basically start the unfolding or folding of the protein. And with terahertz pulses, you look at the kinetics of their folding and unfolding. It turns out the terahertz actually doesn't see the protein. It sees the water around the protein, right? So like this, it was one of the very first experiments where people saw that water actually makes a difference in how the protein folds and unfolds. And so the funny thing about this is in this experiment, if you look how they were following the terahertz pulses, first of all, they could not detect the full terahertz pulses. They only had to sit at the peak because they didn't have enough signal to noise ratio. And second of all, they had to integrate for millions of pulses to get one pulse or one data point because of the low signal to noise ratio. So that means they were probably using an 80 megahertz laser at the driving end, but then they were basically having a resolution of like a second or a millisecond, right? So this is really a shame. So if you had now a high average power terahertz source, you could do this at much higher resolution and at the spectral resolution as well. So this was a little bit, this is the type of experiments we're trying to build now in our lab. And in fact, the vision of what we're trying to do, we're developing all these terahertz sources because we have a pretty clear idea what we want to do, or what I want to do, and I find really this fascinating. If we have these very special high-power terahertz sources, we can consider to do crazy experiments. The crazy experiment I have in mind is I want to do atomic scale spectroscopy inside a cell. I want to see how the water behaves differently as it is in different positions of a cell. Okay, this can be done. Actually, now people do terahertz spectroscopy at the atomic scale, And now what I want to do is just take it to the most difficult case of a biological sample. So this is what we're trying to build up now, which I think will take probably 10 years until something happens, but we are trying. So, okay, so there is a reason why this has happened is people have been using these two types of laser systems for this terahertz science. One is these TISAF systems, you all know, 1 kilohertz, low rep rate, etc. Or then on the other end, if you only need to do linear spectroscopy, then you can use these very high rep rate systems, but then your single pulse cannot do much. So it's only good for linear spectroscopy, right? So, okay, let's take a look now at the final results for terahertz generation in the last 5 minutes. So here are how people are generating these terahertz pulses nowadays. There's ways of generating with photocurrents and semiconductors. There's these so-called spintronic emitters. There's the most well-established methods in Ki2 crystals, and there's even a bit more exotic methods in two-color ionized gas plasmas. I can't go through all the methods, but I want to just convey one message. Every single one of these methods, it's very, very old methods that have been understood in the low repetition rate region, but every single one of them has not been explored what happened and what changes in the physics of the generation mechanism when you start increasing the number of pulses per second. And there's a case, I'll show you just the one example I have in the time I have, where the physics of the generation just change because the temperature changes. And because whatever, in a plasma, you have accumulation effects that happen if you start to go at higher and higher repetition rates. So your actual nonlinear medium can change. And all those things really need to be understood in detail. And so this is a little bit the mission of what we're doing right now. So we started with optical rectification. Optical rectification is relatively simple to understand. So if you have a material with a Ki2 nonlinearity, you have a short pulse, you have a broad bandwidth, you actually mix through difference frequency generation all the spectral components that you have in pairs within your large bandwidth. And that generates a very broad band pulse in the terahertz domain, which corresponds in the time domain, if the dispersion is right, to a very short pulse in the terahertz domain. And that pulse happens to follow pretty much the envelope of your pulse. Okay, so you get these very clean pulses. Now, of course, what you would like is to have what we call group to phase velocity matching. So what happens is, group to phase matching. It's not really phase matching because you're actually matching the group velocity of the near infrared to the phase velocity of the terahertz. And your nonlinear material should allow you to do that, right? So you're hoping that your nonlinear material allows you to do that. So what you would like is that condition happens collinearly, ideally. You would like to have a material with a great high Ki2 coefficient. You want good thermal properties because I'm trying to shoot 500 watts at the crystals. You would like to have a high damage threshold, low terahertz absorption, et cetera, et cetera, et cetera. So this is all that there's a long list of desired parameters from your nonlinear crystals that never happen simultaneously. And in fact, I just point out, for example, one of the considerations, if you look at this group to phase matching, gallium phosphide is a very nice material. It has collinear velocity matching at this room temperature at 1 micron, so perfect for ytterbium. It happens to have horrendous multiphoton absorption. So that limits you. So one thing works and the other thing doesn't work. So that's usually the life that you have to live with. So instead of gallium phosphide, we went for lithium niobate. Lithium niobate is a wonderful material. It has a very high Ki2 coefficient. It has little to no multiphoton absorption, but it has this problem that the velocity matching is not working. In fact, the near infrared goes way too fast compared to the terahertz. So that means you need a way to slow it down. And one way that people have developed already many, many years ago is to say, okay, well, I'm going to slow it down by tilted the intensity pulse front. So that adds an angle, this cosine angle, that then slows down the near infrared such that you can actually velocity match over a longer distance. Okay, so you can make use of the length of the crystal to generate terahertz light. Okay, this comes, of course, it's great. It sounds great in theory, but the experimental complexity increases. And well, your lithium niobate, the main problem it has is it has a phonon absorption. In fact, in most materials, this is what happens. So in the end, you have such an incredibly broad bandwidth that as you're generating the terahertz light, you're very likely to hit a phonon resonance somewhere that will generate loss. Okay, so this is one of the considerations. You also need to look at your material. What bandwidth do you need for your application? Is this bandwidth enough, or are you okay with 1 terahertz or not, right? So, but lithium niobate has actually demonstrated with this scheme conversion efficiencies of the order of 1% at low rep rates. So this was very motivating to us. So we started doing this in what I call the easy world, which is we have loads of pulse energy and we don't go that high in repetition rate. Okay, so we go to lasers, say in the 10 kilohertz up to 1 megahertz. This can be your carbide laser. That's absolutely wonderful for this exercise. Or your DIRA laser if you're looking for whatever, 200 millijoules or something like that. Okay, so, but the principle here is we have the driving energies that we used to have with titanium sapphire lasers. So this really helps to simplify a little, at least the understanding of what's going on. So we did this exercise. We have this laser in the lab, 500 watts. It can be tuned from 10 to 100 kilohertz. You have a massive amount of pulse energy at these rep rates. And of course, you have long pulses, but that doesn't bother you that much in this case, because I told you there's a phonon resonance. So even if we would generate huge bandwidths, most of it would get reabsorbed in the material. So then in the end, you don't care that much as long as you have the peak power. Okay, so we did this setup. This is how it looks. You have your driving laser, you have your transmission grating, your telescope to image inside your material. Then you have actually a set of parabolic mirrors to image your terahertz either into an electro-optic sampling or a power meter. Then you have a probe pulse to measure the pulses, like I mentioned before. And this is what we're getting now. It's actually quite exciting. So at 100 kilohertz, now you can see here, we are getting relatively good conversion efficiency. So we are typically getting in the order of 0.1%. So you see right away our dilemma. I said 1% before, right? Now at high average power, all of a sudden this becomes 0.1%. So something is changing. The pulse energy is there. So we are having additional thermal effects, which you can see actually pretty clearly here. So if you have the two cases, 100 kilohertz and 40 kilohertz, as the fluence is changed, you see that there's a difference. I mean, there shouldn't be a difference, right? This is all nonlinear optics. In theory, it's the single pulse energy that's driving it. But there is a huge difference, and there's obviously more saturation effects that happen as we increase the repetition rate. Nevertheless, this is quite exciting. So we are actually able to pump at 40 kilohertz pretty much with the full pump power of the laser. And we are getting, for example, pulses that look pretty similar to what we are expecting. So we get these type of pulses. You see here the bandwidths we are getting are in the order of 1.5 terahertz. That's quite typical for the pulse durations we have, etc. But so if we look at the average powers that we're getting, they are massive already, right? So this is a community that a milliwatt is a lot, and we are now approaching with these lasers the watt level at these high repetition rates. So this is already really nice. We do have a problem of power handling and these lithium niobate crystals. It is really not easy to handle this high average powers. And so what we need to do now when we think we want to go to the watt level is we need bigger crystals. So the fluences need to get bigger and bigger to accommodate for the thermal effects. And this is causing us a little bit of trouble. So we went then to oxide, and we asked them to grow us a very nice large crystal for this purpose. And now we are thinking, this is what we need. Well, this was what we thought 6 months ago. Turns out the story is not so simple, unfortunately. We have massive thermal gradients when the crystals become larger. So this is kind of an unfortunate thing. So we thought, well, 20 millimeters is okay. So the thermal effects were not so dramatic. 30 millimeters is too much. So we have really huge thermal gradients that are happening when we are pumping with 100 kilohertz and with 10 kilohertz. With 10 kilohertz, even more, because we additionally have still some nonlinear absorption that is happening. So the thermal effects are becoming so problematic that we are not able to pump the full pump power, even by using the largest spot size possible at the highest pulse energy that we have available. So, okay, this is in principle kind of bad news, but we have a way forward. Okay, wait, I'm going to skip this because I'm going to be too long if not. We actually improved the cooling. I mean, this sounds maybe like something funny to do, but it's very simple actually. We're just adding a cold bridge here in order to cool better the other side of the crystal. And this already makes the situation much, much better, both at 10 kilohertz and at 100 kilohertz. So you guys are great engineers and have high power lasers. So maybe someone can explain to me why at 100 kilohertz we have a better improvement than at 10 kilohertz. So I have no idea. We still don't understand. What this shows you is just the data for the thermal effects in lithium niobate are extremely complicated to interpret. These are horrendous experiments that are very costly because we keep having this happen all the time. So we need to really start making, I actually am calling for a workshop of people working with lithium niobate at high energy so that we can actually join forces and think about this problem together, because it's really becoming something where there's so many parameters to change, so many knobs to turn. You cannot get the full picture by simply one group doing these crazy experiments, right? So this is unfortunately what happened to our 30 millimeter crystal. It's good we ordered 2 of them so we can still continue at least for a little bit of time. So, okay. I think I'm already past my time. But so I'm going to finish just with the last aspect. So we had these very high energy pulses now at tens of kilohertz, and now I want to go to the more difficult world. This is the world where we don't have that much pulse energy anymore. Now we have microjoule pulse energies, and we have still these hundreds of watts of average power. So how do we do there? We have a lot extra work to do, and now we are actually using our beautiful thin disk lasers that we demonstrate ourselves. We build the lasers ourselves. We have this typical system in our lab that is operating for years and years. This is a 125 watt laser, around 9 microjoule pulse energy, and a pulse duration at around 580 femtoseconds. And you see it has this beautiful second hyperbolic squared pulses. Everything is really clean. We have the possibility to compress them down. I mentioned this already. We build our multi-pass cell compressors to generate sub-100 femtoseconds and do this spectral broadening. Everything works like textbook. Everything works like expected because the pulses are so clean at the input, right? So it's really wonderful. And so we have this kind of same average power level now with shorter pulses. Now we can do the same trick and do this tilted pulse run in lithium niobate with these lasers and see how far we can go. Now we won't have all this nonlinear absorption, etc., right? So the question is, can we go further? The answer is no. The higher the rep rate, the worse life gets. And there's a simple reason for that if you look at how the terahertz is being generated. In fact, because you have lower pulse energy, you need to make your beam size smaller. In this geometry, your small beam size means there's a huge area where terahertz is being generated, but actually the crystal is not being pumped. So that means all that is being reabsorbed in the crystal, right? So you should think of a better geometry to do this. And so in the end, you're limited by other aspects when you start to make your spot sizes too small in this geometry. And this is in the end another limiting factor. Nevertheless, we get really nice results with this laser. So you can still get record high average power. So we get the 66 milliwatts at 13 megahertz. This is like 3 orders of magnitude higher than anyone has at this really high rep rate. So it's still really interesting and promising for many applications. Okay, so I'm going to skip 2 things so that I can actually go to the conclusion part. So moving forward, how do we do? I showed you a bunch of experiments, terahertz generation with record levels, et cetera, et cetera. Now, how do we move forward? We have this extremely inefficient conversion process. Terahertz is interesting in everything, but how do we move to higher efficiencies? Now, one idea is the following. The thin disk laser has this really beautiful advantage that you have a free space resonator with huge amounts of intercavity power. So why not simply placing the nonlinear medium inside your laser, right? In a similar way to what people do with passive enhancement cavities. So this should work, right? So we have all this laser. Of course, it sounds easier than it is, but we actually did a proof of principle in which we can drive in thin lithium niobate this time, terahertz generation with hundreds of watts of average power intercavity. So this is one possible path forward. Now let's design lasers not for output power, which is inefficient, design them for intercavity power. And then we put our nonlinear conversion there. Okay. The other option, plan number 2, is we go to longer driving wavelengths. Forget, why do I do 1 micron? In the end, I showed you before, my results seem to be pretty much limited at some point by multiphoton absorption in all these crystals. So I don't want to build systems at 1 micron anymore. I want to build systems at 2 microns now, because we actually have good lasers that can do that. So why not doing that? So there's more and more evidence that this should work to increase the conversion efficiency and all these techniques. So, and instead of doing an OPCPA, people have tried to do this, but in all these experiments I showed you before, terahertz generation, record conversion efficiency. This doesn't tell you that at the front end, there's an OPCPA, right? So that's pumped with a 1 micron laser to get 2 micron, and then that pumps the terahertz generation. So all in all, your conversion efficiency is not good. But from the 2 micron to the terahertz is great. So I want to do this differently. I don't want to build OPCPAs. I want to build lasers that directly emit at 2 micrometers. Okay, so how do we go around doing that? There's a variety of options. There's thulium fiber lasers that have made lots and lots of progress. There's chromium-doped transition metals, and there's holmium-doped solid-state lasers. We chose holmium for very practical reasons. We are good with ytterbium. We've built disk lasers with ytterbium, and holmium is just the little sister of ytterbium, so it helps you to have a good laser system that stores a lot of energy. And additionally, the really big advantage of this is it actually works at a sweet spot for transmission of air. So all of these systems suffer from the fact that 2 microns is typically in the atmospheric, not transmission window. So they suffer from humidity in the air. So average power and energy scaling is really, really difficult with most systems. And holmium has a little advantage there. The only problem is it's not like holmium is new. There are plenty of holmium systems out there, but most of the systems that are out there so far is like multi-picosecond pulse durations. So now we started looking at holmium YAG, and then this is actually a really nice material to start with because it's, like I said, the little sister of ytterbium YAG. For example, I tried to put here for comparison what the two systems have. They have similar properties, somehow broader emission spectrum, but more structured, which makes it more difficult to get short pulses. And if you look at the electronic structure, of course, ytterbium YAG is much, much nicer, right? So all these additional levels will make life more difficult when you go to higher doping concentrations. So there are extra challenges there as well. It's not as simple. Okay, so and then I promise this is the last 2 or 3 slides. So we built several systems based on holmium now that work directly at 2.1 micron. Femtosecond or picosecond laser systems. So we are getting now to the place, remember what I showed you at the beginning. The first mode-locked thin disk laser was 16 watts, and now we are at 550 watts, right? So this is one of the very first holmium mode-locked thin disk lasers that are out there that has already 2 microjoules and 50 watts. So now if I go and take this now in 10 years, I'm hoping that we'll be the same place where we'll be at 1 micron. We will see. And there's a lot of variety of things that you can do. You can explore broader bandwidth materials. You can build bulk lasers, etc., all with holmium platform. We have to basically rediscover the world on how to do all this wonderful ultrafast laser technology now with holmium directly at 2.1. I really think this will make life a lot easier for all our nonlinear conversion experiments in the future. I think I'm not the only one who believes this. So, okay, so I'll skip the very latest results because I'll drive you crazy, and I'll conclude. I guess you got that I'm excited about 2.1 microns, so I guess the last slides you can skip. So if you're interested, you can ask me later. So I showed you actually that we really have now a next generation of terahertz sources, which we can drive at 100 watts of average power with ultra-fast lasers. We have really nice results now with lithium niobate, and we have lots of research going on with other methods that share these advantages, high power, broad bandwidth, etc. We have now started to look at first applications that show the potential, but this is really the next step to do. And higher terahertz bandwidth will slowly start accessing the same high average power as we make progress. And I really think this really shows it's one field where it's really beneficial to have advanced high power lasers to really move another field forward. And I hope that, yeah, maybe there are some ideas of what's happening in the lithium niobate crystals from this crowd in which we can actually work together. So I still put the idea out there. If you want to do a workshop on lithium niobate, I'll be very happy. So thanks a lot. And sorry I was a little long. I thought it was actually 1 hour, so I had calculated for 1 hour. So thanks a lot.
So maybe a few questions. We still will have some time.
Hi, thanks for the nice talk. Really interesting. I'm just wondering, there are also a bunch of people, using electronics way to generate terahertz waves, like using electrical oscillators.
Right.
How do you compare your technology and the electronics version, and pros and cons?
Yeah. So the electronic systems are normally, they shine for applications where you need very compact things and where you don't need the bandwidth. So the big difference of these systems is the huge bandwidth that you get, right, with which you can really do very, like, in principle, single shot spectroscopy, right? This is something where the electronic sources, they don't manage, of course, to get those very short pulses. I think that's really the big advantage is the bandwidth, but then the place where we lose is the cost and the size. So this is still something where the terahertz community is like, yeah, okay, but your laser is like huge, right? So we can't mount it on a robot and make it fly around the room or something. So the electronic people are pushing, of course, for more compact and more efficient sources. Yeah.
Okay, I don't see any more questions. So let's thank again our speaker and the sponsorships that is from Light Conversion, and my colleague Dominykas Gudavičius would make a short introduction about the company.
1, 2. Can you hear me well? Yeah, sure. All right, I guess the pointer doesn't work. Oh, okay, it's a bit laggy. Anyway, yeah, so today I would like to present light conversion. And before, I'm pretty sure you had some more technical talks. So this is not going to be one. It's not going to be very technical. It's going to be my path, from the student, how I became a laser engineer. So I would just like to present my story. So my background, I graduated from biomechanics at Vilnius, what's called now Vilnius Tech. And basically, as a biomechanics person, you work with medical equipment from mechanical point of view. So that was my bachelor. During my master's, I went to the Royal Institute of Technology in Sweden, where I basically worked. I studied solid mechanics, which is a certain branch of mechanical engineering. After graduation, I started to work as a finite element analysis engineer, consultant for Scania. I'm pretty sure you know Scania, the company that makes trucks. And one of my main tasks there was to make sure that when a truck crashes the wall, it passes all the certificates. Basically, it's allowed to go on the road. So here you can see one of the car crash finite element analysis, how it looks like. So everything works like it's a simulation, basically, from which you get the stress, the strain, and so on. And then you can analyze if the truck was, let's say, designed properly. And the another company, I'm pretty sure you know Volvo company. So I have a question for the audience. How do you think, how many cars does Volvo crash every day? Okay, per year. Let's say per year. Any guesses? Well, it's around 360. So basically, like every day they crash a car. So it's a huge number, and each car is manufactured, let's say, manually. So it's really expensive. So basically, you want to get as much information as possible before actually crashing the car. So when it actually crashes, it passes the certificates, and you can start mass production. But actually, as an engineer working in mechanical field, I always wanted to do a PhD. And for let's say the best PhD I could imagine would be industrial PhD, which basically you spend time at the university, but you use equipment from the company, and the company benefits from it because it's gets exposure, and you also get the chance to use their equipment and produce make some new results. And I had this opportunity to become an industrial PhD student with cooperation with light conversion at Cardiff University. And so basically, I just went from doing simulations to doing microscopy with laser sources. And here you can see some flowing beads in the water just to show what sort of work I was doing. So those are PMMA beads, and those are polystyrene beads flowing in water. But we're not going into technical details. Yeah, okay. Yeah, and actually you might guess that working as a mechanical engineer and working as a laser engineer is completely different. But when I started to work, I started to see some like similarities. The things that, let's say that I was doing, what's called like modal analysis, where you hit like certain part of the vehicle with a hammer and see how it vibrates. You can actually think, we have like here a Pharos laser, which is like a pulsed laser, and those pulses can work as a hammer. Like you can hit, for example, a molecule with a hammer. So it's like there are some really like similarities that I started to see, which really helped me to like get into the field, because I was already familiar with it from, let's say, purely mechanical point of view. So here you can see a picture of me working in the lab. This is like just the seconds before my supervisor walks in. You know, you just grab some random things, some scissors and pliers, I think, and yeah, I'm working. But yeah, so basically the main thing for me was I switched from purely theoretical work to more work in the lab, which was really challenging, but at the same time rewarding, because when, like, you can also learn a lot of practical skills. This is my first setup that I built. Like, this is the microscopy setup, and once you start working as a PhD student, your main goal is basically to contribute to the general knowledge in a specific field. And but it actually takes a lot of time just to learn new things. But as I said previously, I managed to answer some of the questions I had as a mechanical engineer. I managed to answer those questions by working in the lab with lasers, because you look at the problem from different point, and I think it's really important, and actually it helps you to grow as an engineer in general. So I also had the opportunity to collaborate with other labs. So the person who took this picture of me working in the lab said, like, I look like a gardener, like working with pot of flowers. But in reality, you also learn a lot of, if you have an idea and you try to apply it in your own lab, you learn a lot of other approaches, how other people treat the same problem in other labs. I think it's also really important. Another, I think, really key aspect is taking outside the lab. I don't know how many PhD students do we have here. Okay, we have one. Okay, we have other. I mean, we have a bunch, but I don't know when, I mean, I graduated maybe a year ago. So I think people tend to talk about mental health and so on, like how PhD students tend to wear off. I mean, so I think it's really important to take it outside the lab to build trust, because you work with those people, and it's also very important later on when you're in business, because you're not afraid to ask questions of other students, like your colleagues, the ones that you work with, if you have a specific question, let's say. And yeah, just try to keep the work-life balance. And this actually leads to some results, which is very important. I mean, if you're a PhD student, your main goal is to basically contribute and do as much things as possible, like in your field. But the key thing here is the cooperation between industry and science. Because when you're a PhD student, you work in the labs, and when you're outside the lab, you're like, after you graduate, you work in the industry. So it's so the colleagues that you worked with and stayed in academia, they could really help you by, for example, raising questions. Is it possible that your company can manufacture something like this specific laser? And then you can actually, well, start to get in business with them. But I mean, I spent some time in academia, and I spent some time now in the industry. If you just compare those two things, academia gives you a lot of freedom. Like, you can do a lot of things, basically. If you work with the project, you can do electrical engineering, you can do programming, you can do mechanical engineering. But there's certain career uncertainty. What I felt as a PhD student, well, basically after you graduate from the PhD, you can do a postdoc, but it's kind of hard to get a postdoc and where you should do a postdoc and so on. And your main goal is to produce ideas, but not to develop them like that deeply. You just demonstrate that you can do something, and usually you leave it for the industry. If the idea is really good, then the industry will pick it up. In the industry, however, you work in the kind of narrow field. Well, you do, if you're a programmer, you're going to program. And the career is real certain. I mean, if you just stick your line of work, and you only develop the ideas that are profitable. It's, it's the truth, basically, because you're like, the main goal is the profit, of course. So, I just wanted to show the main differences and why I decided to pick industry. So what's if we compare academia and industry, what's the benefit? Like, what are the strong sides of light conversion? So, light conversion allows you to contribute. As I said, like before, I was a PhD student. I worked with other students in group projects, and they allowed me to contribute. Basically, it allowed to get certain devices that I could use for my experiments. It also creates world-class products. Light conversion has a broad portfolio that people are using, and they're using basically in the top universities all around the world. And you have the ability to develop something new, which was never developed before. Of course, if we see that there's a market for it. So I know what it's like to work in a huge corporation because I work for Scania and I know how things work there. And I believe light conversion still has this, the ability to develop something new in a rather fast way. Maybe it's not ideal, but of course we have to understand it's no longer like 20 people work in the company. It's already what I believe is over maybe around 700, something like this. So it starts to become a corporation, but we still have the ability to develop something new. And for the scientific applications, we have spectroscopy, microscopy, autoscience, and of course some micro machining. We also have, for the industry applications, we have aerospace, electronics, medical devices, semiconductors. So it's basically the lasers are applied in a rather, basically in a broad range. So for the students, there's also a lot of career possibilities. As I said, like it's not all about light, but it's all about, there's also some things, of course, there's things to do for electronics, production, testing, and so on. So there's a broad spectrum of where you can use your knowledge. For the career possibilities, there's a work-study balance. So if you're a student, there's a possibility to work not a full-time, but maybe part-time. The schedule is quite flexible. It depends where you work, but there's possibility to basically try to basically with your studies, try to balance with your studies. And there's a career development plan. So in general, what I just wanted to say that there's always a synthesis. There's always cooperation between science and industry. So I saw what it's like to be a scientist. I made some connections as a scientist. Then I started to work at light conversion. And the students that were once students now are, let's say, postdocs. And they know that I work in the industry. So there's this nice cooperation that for example, I have right now, which I think it's really important for both sides, for science and both industry. So with this, I would like to end my presentation, and I will be happy to take some questions if you have.